over the integrals that I believe all AP Calculus students should know how to integrate. And the first couple, I think we should be able to integrate sine, cosine, tangent, cotangent, secant, cosecant, and all of their inverses, and ln x. Those are the functions that we're going to integrate. So sine x and cosine x are really nice because they are direct antiderivatives that we should know. And the first one is the integral of sine x dx, and that's just negative cosine of x plus c. And the antiderivative, or the integral of cosine x dx, is equal to sine x plus c. So the first two are pretty easy, pretty simple. Moving along to the next two, tangent and cotangent, not quite so simple because we don't have a straight antiderivative for tangent, so we have to break it up into its component parts, sine x over cosine x dx, and then we let u equal cosine x, which is the denominator, and du is equal to negative sine x dx. Solving for sine x dx, we say negative du equals sine x dx, and substitution is going to be negative 1 over u du, and the antiderivative of that is negative natural log of the absolute value of u, but that's cosine x plus c. So the antiderivative, or the integral of tangent of x dx, is equal to the integral, or is equal to negative ln cosine plus c. All right, next one, cotangent. We do it similarly. We're going to change that to cosine x over sine x dx, and then we're going to let u equal here the denominator again, but that is now sine x, and du is going to be cosine x dx, which is straight substitution, so we get the integral of 1 over u du, no negative this time, and that's equal to the natural log of the absolute value of u, but u is sine x plus c. So the two here are the integral of cotangent here at x dx is equal to the natural log of the absolute value of sine x plus c. So the trick to integrating sine and or tangent and cotangent is to change them into their sine and cosine parts. The next two are secant and cosecant. Now secant and cosecant, you have to multiply by a specific factor of 1 that will allow you to create a u and a du. So you multiply secant x by secant x plus tan x, and then when you do that, you get the integral of secant squared x on top plus secant x tan x all over secant x plus tan x. Now that creates a situation where you can let u equal the denominator, which is secant x plus tan x, and take the derivative of that, and you get secant x tan x plus secant squared x, which lo and behold is the numerator. So then we can let the integral of 1 over u du, and then we see that all the time in these trig functions, and so we should know that by now that's the natural log of the absolute value of secant x plus tan x, which is the denominator, plus c. So the integral of secant x is equal to the natural log of the absolute value of secant x plus tan x plus c. All right, now I'm going to take and move cosecant down because that's too little a space here. All right, so moving right along to cosecant, that's going to be a similar arrangement here, except now we're going to multiply it by another factor of 1, which is going to be cosecant x plus cotan x over cosecant x plus cotan x. Now, why do we do that? Because we're going to create our u and our du situation in the integral when we do that. So multiplying that out, I get cosecant squared x plus cosecant x cotan x all over cosecant x plus cotangent x. And I've set myself up here to be able to use the denominator as my u, which is cosecant x plus cotangent of x. And then du is going to be negative cosecant x cotan x minus cosecant squared x all times dx. And then so I see that I have the negative of that, so I have to bring the negative on the outside, and I get cosecant x cotangent of x minus plus cosecant, try it again, a negative du equals cosecant x cotan x, it was right the first time, minus cosecant squared x dx, and that's a straight up substitution. That's a plus, actually. Straight up substitution. So this will be the integral then of 1 over u on the negative out here, du, which is the ln again. So we get the integral of cosecant x dx is equal to the negative natural log of the absolute value of cosecant x plus cotangent x, because that was my original u. So those two are kind of tricky because you have to know the factor of 1 that you're multiplying by. But once you have those memorized, it's no big deal to integrate those. All right, next one, moving right along. Sine squared x. Well, this one we have to use an identity, and we have to remember that cosine of 2x is equal to cosine squared x minus sine squared x. Well, I need, clearly, sine squared. But I don't need any cosines with it, so I'm going to change this to 1 minus sine squared x minus sine squared x, and that's equal to 1 minus 2 sine squared x, and that's cosine 2x. So I'm going to use this version right here and solve for sine squared x. So moving the sine squared x on this side, I get 1 minus cosine 2x over here, and then sine squared x is equal to 1/2 times 1 minus cosine 2x. And in pre-cal, we call this the power reducing identity because we are reducing the power of sine from 2 to a trig function that has a degree of 1. So we use this specifically to integrate. So this is going to be 1/2 on the outside times the integral of 1 minus cosine of 2x dx. So doing that, I'm going to say this is 1/2 x minus, what happens when you take the antiderivative of cosine? You get sine 2x over 2 plus c. All right, so the integral of sine squared x dx is equal to 1/2 times x minus sine of 2x over 2 plus c. All right? So we got to use the power reducing identity here to integrate sine squared. Similarly, for cosine squared, we're going to use the power reducing identity. So cosine 2x is equal to cosine squared x minus sine squared x, as we stated previously. And I'm going to replace the sine squared now. So this is going to be cosine squared x minus 1 minus cosine squared x. Distributing that pesky negative, I get cosine squared x minus 1 plus cosine squared x, which gives me 2 cosine squared x minus 1. And that's what I'm going to use to solve for the cosine squared. Getting that on one side by itself is going to require me to go 1 plus cosine of 2x equals 2 cosine squared x. And then I take 1/2 times 1 plus cosine 2x equals cosine squared 2x. And you might say, well, wait a minute, Mrs. Muller, that looks an awful like the sine squared. And it is, except that it has a plus sign instead of a minus. All right, so I'm going to say this is 1/2 times the integral of 1 plus cosine of 2x dx. And integrating that, just like they did the other one, this is 1/2 x plus sine 2x over 2 plus c. So the integral of cosine squared x dx is equal to 1/2 x plus sine 2x over 2 instead of x minus sine 2x over 2, which is the sine squared. Moving right along here to tangent squared. Well, the trick to this integral is to remember that tangent squared x is equal to the identity secant squared x minus 1. And secant squared x is somebody's derivative, and that's just equal to tan x minus x plus c. So the antiderivative of tan squared x dx is equal to tan x minus x plus c. All right, so similarly to tan squared, we have to remember that the integral or the identity for cotangent squared is cosecant squared x minus 1. Well, cosecant squared x is somebody's derivative, and that's negative cotangent of x minus x plus c. So the integral of cotangent squared x dx is equal to negative cotangent x minus x plus c. Yeah, we're moving right along. So the trick is to use the Pythagorean identities to help you get to two of the ones that you know how to find the antiderivative right away. Moving right along. Well, secant squared, this is really nice because this is just tan x's derivative. Boom, we're done. Nice to have a couple like sine and cosine. Cosecant squared is negative cotangent of x plus c. Boom, we're done because those are straight up derivatives and antiderivatives. Inverse sine. Well, this one we have to integrate by parts. So we're going to let u equal the I in lipid, which is the inverse sine of x. dv is what's left, which is dx. So differentiating the inverse sine, I get 1 over the square root of 1 minus x squared dx. Integrating dx, I just get x. So using the uv minus the integral of v du, we get x inverse sine of x minus the integral of x over the square root of 1 minus x squared dx. And yes, we have to not only use integration by parts on this one, now we're going to use u substitution, and we're going to let u equal 1 minus x squared, because du in this case is negative 2x dx, and I have an x dx on top, so that's really nice. So rewriting this, it's going to be x inverse sine of x minus 1/2 times the integral of u to the minus 1/2 du. Because this becomes, this right here is my du, and then this is square root of u on the bottom, so it's really negative 1/2. So if I do the antiderivative of that one, that's going to be minus 1/2 of u to the 1/2 times 2 plus c. But what is u? Well, I got to rewrite it here. Well, what is u? Well, x inverse sine of x minus 1/2 times 2, which happens to go away. The 1/2 and the 2, and then u is 1 minus x squared. So I'm going to go 1 minus x squared under the square root plus c. All right. Well, actually, this is plus, isn't it? Because this is minus, and then this is negative 1/2, so that becomes plus. Sorry about that. So the integral of inverse sine of x dx is equal to x inverse sine of x plus the square root of 1 minus x squared plus c. If you were a betting person, you would probably bet that the inverse cosine is going to be similar. Well, we're going to let u equal inverse cosine of x, and dv is what's left, which is dx. Differentiating, we get negative 1 over the square root of 1 minus x squared dx. And v is going to be x. And using the formula uv minus the integral of v du, we get x inverse cosine of x minus, but what happens? We've got a minus here, so that becomes a plus the integral of x over the square root of 1 minus x squared dx. And we're going to use u substitution here and say u equals 1 minus x squared. Du is equal to negative 2x dx. And du over negative 2 is equal to x dx. And then what happens is that plus in front of the integral, which I didn't do the last time, has to become a negative. And then I have 1 over u to the 1/2. du. I'll do this in another step. So x inverse cosine of x. And then this is really negative the integral of u to the 1/2 negative 1/2 du, which we just found out. Oh, I got to put my 1/2 out here. Sorry about that. Here we go. Minus 1/2 times u to the 1/2 times 2 plus c. That's what I get for trying to do this at lunch. I know that I'm going to have a class come in here, so I apologize for the speediness of this, but we got to get it done so you have it. All right, so this is x inverse cosine of x. Now this is minus the square root of 1 minus x squared plus c. And if we think about it, it's the opposite sign, because that's plus and the other one is minus. So the inverse cosine of x dx is equal to x inverse cosine of x minus the square root of 1 minus x squared plus c. Moving right along. Inverse tangent by parts again. So we're going to let u equal the inverse tangent of x. dv is what's left, which is dx. du here is 1 over 1 plus x squared dx. And v, when I integrate dx, is just x. Using the formula uv minus the integral of v du, we get this equals x inverse tangent of x minus the integral of x over 1 plus x squared dx. Using u substitution, I get u equals 1 plus x squared, du equals 2x dx. Dividing by 2, du over 2 equals x dx. This is going to be minus 1/2 the integral of 1 over u du, which looks like an ln to me. Let's hope I can get this done. And so then that's going to be minus 1/2 the natural log of the absolute value of what is u? 1 plus x squared plus c. And so that's the inverse tangent of x. Next one. Letting u equal inverse cotangent of x. dv is what's left, which is dx. The derivative of this is negative 1 over 1 plus x squared dx. v is x. Using the formula uv, so that's x inverse cotangent of x minus, which becomes a plus, the integral of x over 1 plus x squared dx. And extrapolating that from the last problem, this is going to equal negative 1/2 the natural log of the absolute value of 1 plus x squared plus c. So the opposite happened because that one was positive or negative, and then this one is going to be, oh, this one's positive because when you've got a negative here, that's positive. So they're the opposite. All right? That's the inverse cotangent. Moving right along. ln x, we're going to let u equal ln of x. dv is what's left, which is dx. du is equal to 1 over x dx. v equals x. Using the formula, I get x ln of x times the integral minus the integral of 1 over x times x dx. The x's cancel, and we get x, the natural log of x, minus the integral of just dx. But that turns out to be just x ln x minus x plus c. So that answers Cameron's question of what is the integral of natural log of x. So that's in a nutshell, and maybe I'll do it again and have it cleaner. But